Well, yeah, I was presenting in the summer on the digital sound card modes, everything except FT8, and had a wonderful time because I just love that topic. This is another kind of favorite topic of mine, but about a year and a half ago, I could barely spell, VNA. This thing is a piece of technology. So what I'd like to do tonight is talk about it from the point of view of not an RF engineer, but in terms of, oh, look at this fancy tool. Let's add this to the toolkit. All right, I'm looking forward to this because every time I present something on the Nano VNA, I learn a little bit more, especially from the questions and readings. So it's an evolving topic for me. I was not a natural at this. Part one tonight, I'll just try to hit the basics. And then there's a lot to this device that I didn't want to talk about because it gets into the weeds, so to speak. So if this session goes well, and if I'm invited back for a part two, I'll do a what's under the hood. How do these things really work? What do they measure and what do they calculate? So two parts, part one tonight. So one approach is just treat this little gadget like other tools, except, it doesn't look like the tools in the toolbox, but, just pick it up, plug it in, get a device to send some drivers to your computer and see what you can learn. And that's been my approach. I didn't have anyone professionally teach me about this thing. I was in communication with a couple of other folks who really do know a lot about this and guided me. So here we go. Part two, maybe, we'll see in the future, what's under the hood here. There are things called calibration planes, Smith charts, complex impedance, reflection coefficient, return loss, and the one we're familiar with, SWR probably, phase, and phase. That's the key to how this thing works. And when you look at antennas, there's two things that you can measure: resonance and where the SWR is lowest on your antenna. They are not the same thing. And finally, when you use it to try to improve your antennas and you find various degrees of reactance, how do you correct that, either in your shack or up at the antenna? So that's part two. A friend of mine had one of these, and I said, oh, I want to play with this. A Smith chart slide rule. That goes way, way back. I have some friends who do teach engineering at Drexel, and they said they don't teach Smith charts anymore. It's like slide rules. So I thought, let's start with this. Bats, dolphins, submarines. They all emit something, and from what comes back, they learn something about their environment. I thought, that's exactly what this little VNA is. Now, bats, dolphins, and subs, we're talking about sound, sonar. And with the Nano VNA, we're talking about, RF. But the idea is the same. And here I think we can visualize. I lived and worked at a school that had a lake, and we did have bats at the lake. And it was fun to go down there just around sunset and watch the bats come out. And you could hear them chirp, 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 really, really high pitch. And that's how they detect their food. And I guess, bats have two ears, so they can echolocate. And evidently it works very well, or at least the bats who had good hearing ate better and probably reproduced better. Dolphins, the same thing. They can find each other. They can find food. They can find all kinds of things. And of course, submarines, ping, ping, finding all kinds of things in other submarines. That's kind of what this thing is, the Nano VNA. So that's my analogy to the sound waves, listening to what comes back and learning something about your environment. So basically, the VNA, Vector Network Analyzer, can send out a signal on a cable, and depending on what that cable is connected to, some information comes back on the same cable, reflected wave. And in the case of an antenna, a lot of that energy gets radiated and doesn't come back. But in terms of sending a signal into like a filter, you can get some energy going through the filter and analyze that. So there's kind of like two paths that you can use to analyze circuits, a reflected path and a through path. So this is as technical as I'm going to get. I didn't make up the slide, but it sort of shows you in block diagrams what we've got here in this little Nano VNA. So a source, a little transmitter, a milliwatt, maybe less, sends a signal out on a cable to some device you want to test. I guess that's an engineering term, a device under test, a DUT. Some information might go through that, the through signal, and then you can analyze that, compare it to the incident signal. Some might get reflected. So for instance, if the DUT is an antenna, all you're going to get is the reflected stuff. The stuff that gets radiated, this little Nano VNA doesn't pick up. And you separate the forward and the reverse, and you compare them, and there's all kinds of electronics in here. And then you can detect something and display from the information all kinds of pretty graphs. That's essentially what it is. So in block diagram, it looks very simple. The first group that I talked to, the questions were, isn't this like a spectrum analyzer? I had to think about that because I have some spectrum analyzer. The short answer is, well, yeah, they both are complicated, a lot of knobs and stuff, and often very expensive, but they do different things. Spectrum analyzer gets a piece of a spectrum and then looks at it in detail, maybe demodulates it. The network analyzer is a transmitter first, and then it looks at what comes back. So it's a completely different principle, although I see there are some similarities here. So I went on the internet and wanted to find out more about network analyzers and came across a couple. Here's one that I thought, oh, I'd love to have that in my shack, but it costs about as much as my car. So, you know, as a retired high school teacher, I'm not going to afford one of these. Very, very beautiful piece of equipment. Then I kind of looked at what's inside and read some reviews of it. Then I came across this one and I thought, oh man, what? Look at this. Now, the first time I gave this talk was a little over a year ago, and it was the Pentagon Amateur Radio Club. I don't know how my name got tossed in the Pentagon Amateur Radio Club, having taught in a Quaker boarding school, but it was an interesting group. And as I showed the slide, one of the participants interrupted me and said, I use this at work. And I said, you use this at work? He said, yes. I said, where do you work? He said, well, I align the radar systems on F-22 jets at Andrews Air Force Base. I said, oh my gosh, and you're familiar with this? He said, I use it every day. I said, do you get to take it home and check out your antennas? He said, no. He said, the Navy wouldn't like that. He said, besides, I don't like to mix work and pleasure. But I thought, wow, someone knows how to use this thing. Up to 20 gigahertz while we're talking about radar systems on fighter planes. All right, so we're back to the Nano VNA. This isn't quite as impressive in some ways. I think when mine was given to me, I think it cost the club about $50. And I think with inflation and whatever, the prices are going up to maybe $100 now. And mine came about 16 months ago. So I had about a month or two to learn something about it and then present to our local club. So very, very clever gadget here. And there's a lot of companies making them. A common question is, where do you recommend I buy one? I can't. I didn't buy mine, and there's so many different, companies. I think they're all in China, producing these at a price. But this one, at least the one I have, 4 traces, 4 colors, touch screen, battery operated. I mean, there's a lot of electronics here for $50 or $100. I found as I started to learn to use this, one of the limitations is, at least the one I have, a year and a half old, it has internally about 100 data points. So you can't do a wide frequency sweep of an antenna or something, but you can sweep 80 meters, 40 meters, 20 meters. But you can't sweep like, 100 to 500 megahertz. You just don't have enough data points built into the machine itself. The frequency range is tremendous, covers, all the ham bands. It has 2 channels. I'd call it channel 1 and channel 2, but I guess the engineers like to call it channel 0 and channel 1, thinking binary. You also have the ability to measure the signal coming back to the same jack. So channel 0 is a transmitter and a receiver, and channel 1 is just a receiver. So whatever the device you're testing, you can measure the energy that comes back or the energy that goes through it, the way you set it up. It does both very well. But you learn different things about your device under test. Some of the newer ones are coming out with better cases, a little bigger displays, a little more memory, and N connectors. The connectors, I think, are the weak link on one of these because they're just, small. And as you attach cables to them, you're likely to eventually break them off. So I think this one was something of the order of $100, $130, still very inexpensive. So one of the things you have to learn how to do using this device is calibrate it. And you think, I don't have to calibrate my little MFJ meter and comets. Why do I have to calibrate this? It's a different principle. A calibration does not take long, 5 minutes, but you have to do it over some particular frequency range, like the 80 meter band, 40 meter band. You can calibrate it over a wider bandwidth, but then I think you're forced to use a computer controlling this to store all that data. It doesn't have a lot of memory inside it itself. But calibration is essential, but only takes a few minutes. Once you calibrate it, you can save that calibration. So every time you pull out of the box and take it out in the field, you don't have to recalibrate it. So here's the calibration standards. They're built into these little SMA connectors. So you have an O, an S, and an L. An open means the pin and the shield don't touch. A short, the pin and the shield have a little wire connecting. And the L, that's the key. The L is the load. Most cases, we calibrate this based on 50 ohms because that's 50 ohm coax, 50 ohm impedance output on the radios. 50 ohms kind of a common. But you could calibrate it with any standard, 600 ohm, anything. I'll talk a little bit more about why this is so essential and some of the subtleties of this if I give a part 2 under the hood, but I don't want to get too involved in the calibration aspect of this. The calibrations just plug on the end of the little SMA, you punch a couple of displays here, and you calibrate it over some frequency, and then you can save that file. So you can, let's say, save and call it 80 meters, save 40 meters, whatever that's doing. It's really quite easy. The device itself, at least the one I have, only has 100 points for the calibration. And it has a limit of you can save 5 files. That's pretty limiting, but I think, the next generation that comes out will have more memory and more ability in that regard. So I found as soon as I looked on the internet for ways to control this, it changed my life because it made it much easier to read, bigger display. I'm kind of red-green colorblind anyway. So a standard computer connection with a USB cable, you can make larger calibration files. You get really high screen resolution on your monitor. You can collect a whole lot more data on whatever test you're running, multiple graphs, which I'll show you. It makes it much more usable. But you can use it with its own little display, especially on something like field day. Calibration files. So once you use software like VNA Saver, it's free, you just play with how this calibration works, and in a few minutes you kind of figure it out. I didn't have to read any help files, and I've never used this gadget before. So you can calibrate with many more points. This particular one had 2,000 data points instead of 100. And you calibrate it over some frequency range. And when I save these, for instance, I call it over here 10 to 30 megahertz. Calibration 1 to 500 megahertz. Of course, that's a 600K file here. Takes a lot more memory there. And, a calibration for 2 meters or 440. This one I use a lot, calibrated from 1 to 30 megahertz. So one of the things you can do with this, though, is let's say I have in my shack 100 feet of coax, then it goes to an antenna. What I can do is just take 100 feet of that same coax and do the short, the open, and load calibration at the far end of the 100 feet, which means what? I've calibrated this thing, and internally, it nulls out the effect of the coax. That is, what do I want to discover in my shack? I can look at the impedance, the resistance, the reactance in my shack at the end of cable, or I can say, well, if I took this little device way up at my antenna, what would it read? Here, I can calibrate it at the end of my coax, and what I read in my shack reads as if I were up at the antenna itself. Very, very clever. I can't do that with, the MFJ and the comet meters. The other thing, it can actually do this electronically. If I tell that VNA Saver software what kind of coax I have and the length and the velocity factor, it can juggle what it's going to show me based on what it is in my shack, what it is 20 feet away, 50 feet, 100 feet. I can predict what the SWR, the reactance, the impedance are anywhere along the coax. That was really cool. I was very impressed with that. So what happens is when you send a signal over coax, and if you look at what's happening to the voltage and current along the line, unless you have a perfect antenna, the SWR is 1-to-1, the voltage and the current vary over the length of Feedline. I'm thinking about coax. So the impedance varies. Oh. So the resistance reactance varies. Oh. So the resonant frequency varies. Oh, real? Oh. So all kinds of things change because of your Feedline's really kind of part of the antenna. So this is clever enough internally to be able to juggle that as long as the software knows what kind of coax you have. This is a very clever little addition to these things with SMA cables, because it convert the SMA over to the standard size, PL259. Someone said that these don't work very well above 2 meters and especially 440 because the impedance of these cables varies, and these little sockets that we call the SO239s really aren't so good at UHF. So if you want, you can buy the cables to convert to the N-type connectors or figure out something else. So the big question was, why do I want one of these? And frankly, I did not buy mine. It was a present. It was given to me by a local club, and they said, learn how to use it and teach us. So that's exactly what I did. Had a lot of fun learning about it. And here it is, just about a year later, I'm still learning a lot about it. So if it costs about 50 bucks, is that worth it? Well, I thought, well, I don't know, what else could I buy for 50 bucks? And when I was a scout back in my teen years, I was given one of these Swiss Army knives. That's about 50 bucks today. Swiss Army knife. It had all these gadgets on it. And I thought, oh, this is just so cool. When camping, I always had it in my pocket. But I actually just used 1 or 2 of the blades. I didn't use the corkscrew and the nail file and the can opener and everything. So I liked having it, but I didn't really use it to its fullest extent. I think we might find the NanoVNA is a lot like this. It has more potential than many of us are willing to learn how to use, maybe. But it's kind of complicated. And I thought, well, the other thing, especially at my age, it's sort of like a stethoscope to your heart. If you listen to your heart and you know how to interpret that boom, 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 you know something about your heartbeat. So, a stethoscope tells you a little about the health of your heart if you're trained to listen to that. And the Nano VNA sort of can tell you a little about the health of your antenna, if you're used to reading those charts, that information. I thought, let's carry this one step farther here. So it's sort of like an EKG. Now, I'm just at the age now when I visit my cardiologist once a year, I get strapped up and get an EKG, and he knows I'm a retired physics professor. So, this thing comes off. Well, it used to come off the paper. Now they don't even do the paper. But I'd say to him, how about if I read my own EKG? And he says, go for it, professor. And I know a little about EKGs. So I'm describing, this and this and this. And after a minute, I'm feeling very proud of myself that I can read my own EKG. And I said, how did I do? And he looks at me and says, not bad for a third grader. I said, well, that's a compliment. He said, professor, you're looking at the amplitude. You need to look at the phase. I thought, phase. Oh, it's just like antennas, phase. The timing issue, the width of these pulses, not the height. I was very proud because my QRS was up and down, and I have a real good heartbeat. And he said, no. You want to look at the phase, because in my particular case, I do have somewhat of a problem. But it's not the amplitude that's the problem, it's the phase. Okay, so this particular Smith chart, I don't want to go into gory details and interpret it for you, but if you saw this, and this is my 80-meter antenna, 150 feet behind me in my backyard, if you saw this Smith chart, and it has 6 markers, and you see where the markers are, 80 meters, 3.5 megahertz, 3.6, 3.7, and look, it's a little spirally Q here. If you saw this, could you interpret it? If your answer is yes, then you can tune out and do something else for the next hour, because you already know quite a bit about what this Nano VNA is capable of showing. But it's sort of like, what in the world is this? All these that's a weird graph. So if I just saw this, I could say You know, I'll bet this antenna is going to really work well at position 2. Position 2, that's here, dead center. Why? All right, that's coming. I hope before the end of the 45 minutes here, you'll have some idea. Why is position 2 going to really work well on this particular antenna? 3.6 megahertz. By the way, that's, you know, the digi part of the band. Now, what if I showed you this? Whoa, wait a minute. What is this, Professor? A phase graph of an antenna. Yeah. If you could see this and say, oh, man, look, this is phase in degrees. I'd say degree, I'm talking about an antenna. Yeah, phase in degrees. And here's frequency, 80 meters. So here's that same 80 meter antenna. So look, it starts out close to 0 and goes way, way negative. Negative 190 degree phase at 3600 kilohertz. And then gazip up here to positive 190 degrees and then slides back to. What is happening here? If you can tell me, interpret this graph, you know a lot about how antennas behave, reactance, and a keyword, resonance. So normally I'd stop and say, how many of you raise your hand if you look at this and say, I know what this is, but we don't have time to do that. So how am I going to use this little Nano VNA? I can measure all sorts of things. I can get over my head too and not realize what I'm measuring. Resistance. Well, most of us feel comfortable with that word, resistance, ohms. Yeah. Resistance. Something is limiting current and obstruction. Reactance. Well, it's a little trickier. Reactance occurs because of timing issues, phase, capacitive and inductive reactance, and then you get all these formulas and stuff. Impedance. Well, what's an impedance of an antenna anyway? When I taught that in high school, they would call it impedance, but that's a different story. Phase in antenna is like, what's phase in an antenna? Now, the three terms that we should be familiar with, but as hams we really are, reflection coefficient, that's an engineering term. Return loss in decibels, another engineering term. SWR, only hams talk about SWR. Engineers don't use that term. And finally, the Smith chart, we'll come back to that. So that's what I want to talk about a little bit in part 2 to get into more detail of what's the thing actually measuring, you know, like the heartbeat, the EKG, what does it measure? And then what does it interpret? What does it figure out and show you graphs? So I'm going to use an example. And here's my antenna in the backyard. One of, I think I've got 14 at the moment. Oh, they come and go. My wife owns the front yard. Beautiful, all these flower gardens and everything. I own the backyard. There's more aluminum than flowers. But I realized something too. Antennas, when they get too close to each other, they interfere with each other. You dummy. You know, it's like, yeah, of course. All right, so I've got 135 feet of wire fed with really nice, you know, sparkling new RG213, $150 for the cable, right? A W2DU balun. We won't go into what baluns are. And I want to know, what bands can I use this? This is a great antenna. It's up in the trees. So can my Nano VNA sort of guide me? Where will this antenna work? Well, 135 feet is a clue, isn't it? What else? So I hook it up to my Nano VNA. I hook it up in my shack at the end of 150 feet of coax. And I say, all right, Nano VNA, plot the SWR from 3 to 30 megahertz. At least I understand SWR. At least I think I do. And here's the graph I get. And by the way, this takes about 30 seconds to get the data and show me the graph. Now, this is the graph on the software, not the graph on the little, 4-inch display. So what do I see? Oh, man, here's SWR, 8 to 1. Well, that's no good. 5 to 1, that's no good. Oh, but here's 1 to 1. Well, right at the low end of 80 meters. Perfect. Whoa, well, I like that. It's 135 feet long. That's a clue. And then bumpity bump, lousy. Oh, here it's, man, I can use the antenna here. Low SWR. Oh, no. That's 11.9 megahertz. My license doesn't let me operate there. That's, by the way, what? The third harmonic. Blah, blah, blah. Not very good. Oh, man, look at this. Beautiful. I can operate 19.2 megahertz. Oh, no. I don't have a license there either. So you see the problem. When I ask the question on 135 feet antenna, where's the resonant frequency? Everyone jumps, 80 meters. But it's also resonant on harmonics. In fact, it's resonant on gazillion frequencies. But it may not work well with coax Feedline at gazillion frequencies, or the resonant frequency may be a band I don't have the license to operate there. So I thought, well, that was pretty cool. Now I kind of knew my 80-meter antenna wasn't going to work well on 40 and 20 meters coax fed, but it was kind of cool to verify this with my NanoVNA. So here's the main problem with 80 meters. It's a wide band from 3.5 to 4 megahertz. And the SWR, if you even cut it for the middle of the band, it often goes pretty high, 3, 4, 5 to 1 at the ends of the bands. We'll come back to that. So there's a key question that at least we all have to have a common knowledge of. What does resonance mean with an antenna? Resonance. I hear that term all the time. So normally I'd say, all right, call out your answers, but we're not going to do that tonight. So just think for a minute. How would you define the word resonance with respect to an antenna? Because I'd like to go into this in a little more guts. So at resonance, here's the way I see it. At resonance, the feed line current and the feed line voltage are in phase. The current's on the antenna and the feed line's carrying the information up and down to make the antenna currents move. At resonance, they're in phase. Oh, remember I said phase, phase, phase on antennas. Why is that good? Because you get the maximum current at resonance. Why is that good? Because more current means more RF radiation coming off your antenna. Now that's a gross simplification. I'm not suggesting antennas won't work off resonance, but this is the ideal, and this is what resonance means the way I view it. At the resonant frequency, the reactance of your antenna is a magic number. What's the magic number? 0. No reactance. That does not imply the SWR is lowest, because you might have a resistance of 1,000 ohms. That's not going to work well 50 ohm coax. So this was a nice graph because it gave me a little perspective. The resonance of a half-wave dipole up in the tree, you know, people say, oh, it's 50 ohms, 60 ohms, 70 ohms, 45 ohms, but it's something pretty low. That depends on the height above ground, especially on an 80-meter antenna. When I first set my 80-meter antenna up in the backyard, I mostly do NVIS, the local skip. And I thought, I'm just going to put it 10 feet above the ground and see what happens. It's easy to do. Put it on a couple of poles, 10 feet above ground. So I measured, and the impedance was about 15 ohms. The SWR was like 4 to 1. That was the best SWR I could get. I thought, oh, that's not very good. What did I do wrong? So I lifted it up to 20 feet, and everything looked better. Brought it up to 30 feet, and everything really looked better, and I let it stay there. So there's kind of a height relationship here above ground. Why? Well, because the ground's somewhat of a reflector. The radiation goes down, comes up. The reflected energy hits your antenna. So it's like wham, wham. And sometimes they interfere, and you can get a very low impedance at your feed point. So generally, as you lower antennas, the feed impedance lowers as well, as low as 10 ohms or something. What if I don't feed it in the center? What if I feed it off center, like 1/3, 2/3? There's a very famous antenna now called an off-center fed dipole. So if you feed it off center about 2/3, now the impedance is about 300 ohms. Oh. So in other words, with a given length wire, the impedance, not the resonant frequency, the impedance depends on where I feed it. What if I end feed it? I had an end fed up for about 1.5 years till I finally burn it up. An end fed has a really high impedance. You're feeding at the end of the antenna, and you might say the antenna doesn't like to do that. End fed antennas have an impedance of thousands of ohms. So if I'm using 50 ohm coax, that's not going to work well. So you need to connect it to some sort of an Unan 49 to 1, 9 to 1, whatever. You need to match the coax impedance to the antenna. So I thought that was kind of interesting. The Nano VNA can tell me a lot about this. So a center fed dipole. Okay. Here's the current distribution. An off center fed dipole, you get the same current distribution. An end fed dipole, you still get the same current distribution. So the resonant frequency does not depend on where you happen to feed it. It depends more on the length of the antenna rather than, now the feed point does depend on, the impedance depends on the feed point, yeah. So I thought, how am I going to explain this? I was a former 9th grade physics teacher, so I had to really think basic. So I thought, this is really a good analogy. I'm a Grampy, take my grandkids to the park. They jump on the swing. Everybody knows what my job is. My job is get my grandchild going. So doesn't this look to you like an end-fed dipole? As soon as I thought about this, I thought, oh, this is a good analogy. What's Grampy? Grampy's the feed line connecting back to the radio. What's the kid on the swing? That's the current on the antenna conductors. All right, so the question is, how does Grampy know when to push? Oh, come on. Even grandkid knows. So when should Grampy push? Well, if you push it just the right time, you're going to have a happy grandchild. If you push it at the wrong time, you're going to have a collision and not so much fun. So grandkids know that. So even young kids would say it this way: Grampy, push in phase with my natural period of swinging to increase my amplitude. Now, she doesn't use those words, but that's what she'd basically tell me. She'd probably say, get with the program, Grampy, wake up. Stop talking to your neighbor, Grampy. Pay attention, Grampy. She wants to swing higher and higher and higher. Meanwhile, I'm thinking, push. And if I'm not paying attention and I push too soon, I crash into her, and that's no good. So you see what resonance means in this situation? Grampy has to push at just the right time. Why? Because then the amplitude of the kid will increase. Why? Because the energy is in phase between the feed line, Grampy, and the antenna current, grandchild. So that's the way antennas work. At least that's the way I like to visualize. The input push from the feed line, that's Grampy, should be in phase, timing, with the natural vibration of the current along the antenna conductor to get the maximum current. Maximum current, maximum radiation, everyone's happy. That's resonance in an antenna. The timing is correct. How can my little $50 Nano VNA tell me, Grampy, when to push? Easy. The next slide. All right, so let's look at another analogy. Here's some, I forgot. I had the tuning bars, and they're downstairs on my kitchen table. I forgot to bring them up. But you get the idea here. Tuning bars, they're all made of the same material. They're the same thickness. They're mounted on wood just so they sound a little better, but the longer bars are the lower sound pitch. The shorter bars are the higher pitch. Why is that? All right, I'd love to have a 5-minute discussion. Why does that happen? It has to do with the fact that the length of the bar, the vibrations have a shorter distance to travel, so the period is shorter. The period is shorter, the frequency is higher. Oh, is it that simple? Yes. How about an antenna? It's the same thing, except it's not sound. What's happening on antenna? The current's going back and forth from the feed line to the end, back and forth, back and forth. So if it's a longer antenna, it takes a longer time for that current to get to the end, your insulator, and then return. So a longer antenna has what? A longer period of vibration, talking about RF now, and a longer period is a lower frequency. There you go. So resonance is kind of the natural vibration of the object when you hit it. Now, we're getting into some buzzwords. Reactance. I'm not sure I wanted to talk about this, but I thought, oh, let's go for it. So what happens on my antenna if I operate a too low a frequency? I'm operating below like my 80 meter antenna. What if I try to operate at 3.52 megahertz? Okay. The dipole is too short. Okay. What does that mean? If I cut my antenna for the middle of the band, 3800, and I operate at the low end of the band, the antenna needs to be longer to work at resonance, but I'm not going to go climb up the antenna and add 10 feet. What does that mean? It means like the kid on the swing. The current's leading the voltage. Kid on the swing is leading Grampy. We call that capacitive reactance. A fancy word, capacitive reactance. Timing's wrong. What if I operate at the top of the band, 4 megahertz? Well, now it's the reverse. The dipole's too long. I need to shorten the dipole by 15 feet. Well, I'm not going to go cut off 15 feet. So now the current gets behind the driving voltage, and we call it inductive reactance. And there's formulas for this and blah, blah, blah. The important point is what? In either case, you got a problem. Grampy isn't pushing at the right time to get the maximum current for the grandchild. So I had to throw this slide in too, because the last time I talked about this, someone interrupted me and said, no, my dipole works fine off resonance. So I said, all right, so I'm going to add a slide. Does the antenna itself need to be resonant to work well, especially on 80 meters? And anyone who's worked that band knows the answer is what? No, the antenna doesn't have to be at the resonant frequency. Although if it's not at the resonant frequency and you're feeding it with coax and you have an SWR 4:1, you may plug that into your transmitter and it might balk. I see some smiles because 80-meter operators know this. Why 80? It's always 80 meters. It's always the fisherman from Gloucester. And I fished out of Gloucester in the summer of my sophomore year, so I understand Gloucester fishermen, at least back in the 1960s. So no, the antenna doesn't have to be resonant. But in order to make the radio happy, the radio wants to see a load of 50 ohms impedance, no reactance. Well, my antenna isn't going to do that. However, if I put in this little magic gadget called an antenna tuning unit, an antenna tuner, I can fool the radio into thinking, hey, here's 50 ohms. Does that make my antenna work better? No, not necessarily, but it makes the radio work a whole lot better because the full power can head up towards the antenna. So no, antennas don't need to be resonant, but if they're not resonant, you may need a little tuner either in your transmitter or beside your transmitter. Now, my Nano VNA is a great way to find out where the resonant frequency is. Because here's an example of a little MFJ tuner, and instead of my transmitter, I hook up my Nano VNA tuner. The output of the Nano VNA tuner goes into the tuner. The output of the tuner goes up to my antenna. And instead of transmitting 1 or 10 watts, I'm net control on it's Sunday morning, by the way, 7:30 a.m., not p.m. So that Pennsylvania NBEMS, we cover within 300 miles of Philadelphia, and half the stations checking in now just to see if I can hear them, use 5 watts. And I can hear them. 5 watts on 80 meters. If you don't have much noise on the band and there's no thunderstorm going on, it really works well. So instead of tuning up with your radio, how about if we tune up with our 1 milliwatt Nano VNA? So then I'm not going to, QRM the net. Yeah, I can say to the Nano VNA, just keep pinging at 3550, 3550, 3550. And I'm looking at the little chart here, and I can adjust the antenna inductance and capacitance to get that right into the bullseye, which means 50 ohms. So really easy to use my Nano VNA to help me tune the antenna. And once I find that frequency and it works well, I just make a little 3x5 card and write down the settings. Of course, some of you have, a Kenwood TS590 and you don't worry about this. You just press the tuner button, bzz, bzz, and it does it for you. So a lot of the modern radios obviously have built-in tuners. All right, here's another example, and a lot of folks use something like this. You just remove the coax, feed it with balanced ladder line, 450 ohm. It's actually a lot cheaper than coax. And in one sense, it works a lot better because it's a lower attenuation. You don't lose as much energy with higher SWR. So like a 100-foot, 300-foot antenna thrown in the trees, in the clear, fed with 100 feet of 450 ohm ladder line. It's got to go to a tuner and then to your radio. And the SWR on your radio looks like it's very low. In fact, you tune your antenna tuner so your radio is happy. Meanwhile, what's happening out here? Where this feed line attaches to the antennas, the SWR adjusted there? No. Have you made it any better anywhere along the line? No. You've only done one thing. You've made the coax cable have an SWR of 1:1. So now your radio can deliver its full 100 watts. It's a little more complicated than that, but you get the idea. Here's a really simple antenna. Just throw 100 feet of wire into a tree, feed it against ground. 10 through 80 meters, this often works. Depends on your ground, doesn't it? This question came up. A lot of folks have SWR meters and think, well, why do I need a Nano VNA? I have one of these gadgets. And actually, this might cost as much as, the Nano VNA or even more. Okay, so it gives you the forward power, it gives you the reverse power, and where the two needles cross gives you the SWR. So it does tell you a lot of information. What if it says my SWR is 3:1? I think, oh, that's not very good. It doesn't tell me anything about how to improve it. I'd have to interpret that and go up and play with my antenna, come down and check it again. This is kind of a very dumb device. It just gives me a relative reading of what's coming up, what's coming back. There's no phase information, very limited. And even though it looks like a very nice piece of equipment, doesn't tell me as much about how to improve my antenna. So if I put a SWR meter right at the antenna feed line and then have another one in my shack, do I learn any more information by having 2 meters? One in my shack and one at the antenna? The answer is no. No. The SWR doesn't change on your feed line. Oh, wait a minute, professor. My SWR changes, I know. And I had 2 people tell me this, and they were both very adamant. They said, you're just wrong. The SWR changes as I go up my feed line. I said, okay, let's do this. And I said, I don't know what band you're operating on, but do this. While you're transmitting and you're looking at your little SWR meter, with your hands, grab your coax and move your hand up and down the coax. See if your SWR changes. This was a live talk, local club. And 2 of them did this, and they said, by golly, the SWR is changing with my hand. I said, okay, I'll predict your antenna is a J-pole. And they both had J-poles. I said, why did I know that? Because often on a J-pole, you get reverse currents because you're essentially feeding an antenna that ought to have a choke or a balun next to the feed line antenna combination. So in 2 out of 2 cases, I was right. I said, well, you also might get some problems in your shack with the RF coming back down. Sometimes you touch a microphone, you get a little shock, touch something, Anyway, you don't want RF in the shack. But an SWR meter tells you very limited information, whether it's up at the antenna or down in your shack. It's better than nothing, perhaps, but it doesn't tell me anything like a Nano VNA. How about these? Oh, man, look at these. These are very nice instruments. They're also big bucks. What's wrong with this image? This is a nice MFJ meter. I have one of these right up next to me here. What does it say the SWR is right over here? 1-to-1. Look, SWR 1.0 at 20 meters. Resistance 50 ohms. Couldn't be get any, 3 ohms reactance. Can't get any better than that. Look at the antenna. Wait a minute. There's nothing connected here. That's impossible. How did they make this? I don't know. They did a little Photoshop editing here. On 20 meters, 14 megahertz, without putting an antenna on these, you're not going to get a 1-to-1 SWR. So MFJ, you faked it. So let's check out some other things with Nano VNAs. Measure cable length. I can measure all kinds of things about coax. Here's the output, right? Channel 0. What if I attach this to an unknown cable? I can do what's called a time domain reflection, TDR, fancy word. Means I send a signal down and wait to see what comes back, a TDR. I can actually do that with a signal generator and oscilloscope. I used to do it that way, but this little device does it faster and better. Essentially, what I can do is measure the length of an unknown piece of coax. Well, that's cool. I could also get out a tape measure and measure it. But I thought this is kind of interesting how this works. You send a pulse at one end of the cable, wait, and see what comes back. Time it. So that's what this device just did. And here's some data on the vertical axis and some data on the horizontal axis. And the horizontal is time converted to distance. Well, wait a minute. How did my $50 Nano VNA know how to make this? Well, I told it I've got Belden RG8X, and it's the Belden 9258, has a velocity factor of 82. 82% the speed of light is the current. And look at this, no return, no return. Big return here, 17 meters away. Well, 17 meters, that was about, what, 50 some feet. And I knew it was, 50 feet of coax. So not only that, but look, there are no bumps here. So I don't have a break in the cable. I thought, well, can I use this on 6 meters? I was putting up a 6-meter antenna. So I thought, well, let's send a signal out instead of measuring the time. Let's measure how much signal comes back. How do I do that? Oh, look at this one. Here's an attenuation. So I'm measuring the return and how much the return loses because it's got to go to the end of the cable and then back again. So it's like a 2-way loop here. Well, the return loss is in decibels. All right, so you have to be somewhat familiar with the decibel. So down here at 1 megahertz, the loss is half a decibel. That's meaningless. At 20 meters, the loss is a little more than 1 dB. That's still meaningless. How about at 6 meters? That's here, 50 megahertz. Oh, now the loss is 3 dB. Why? 3 dB is getting pretty significant. That's half the voltage. That's a quarter of the power. So I don't think I would use this cable 50 some feet on 6 meters, or worse at 2 meters, or never at 440. But yeah, I could sell it to a CB operator for 11 meters. It can measure other things as well: inductance, capacitance, resonant frequency. So what it can do is measure a signal that comes out, goes through some test circuit. And I'm going to just say inductor and capacitor. What comes through, I can measure in channel 2. What should come through? Well, this is a circuit. Some frequencies are going to get blocked. Why? Well, because capacitors and inductors behave in opposite ways. High frequencies like to easily get through capacitors. Low frequencies can get through coils. So it can measure things called resistance, reactance, impedance, and phase, and it does it very well for $50. So just a quick digression, then I'm going to stop. Coils. Well, coil is what it says. It's just a coil of wire. So what? Well, by making a coil of wire, when you send a current through this and it goes wrapping around, every time a current goes through a wire generates a magnetic field in a certain direction. You can use the right-hand rule for that. Oops. So for AC, it works a little differently because when the current goes in one direction, a coil makes a magnetic field. When the current reverses direction, that magnetic field has to collapse and rebuild itself in reverse polarity. So I used to tell students I taught this. You might try this. Hold one finger up and wag it as fast as you can. That's pretty easy. Now wag from your wrist. That's harder. Now wag from your elbow. That's really hard. Now wag from your shoulder. That aches. That's like inductance. More inductance means there's more resistance to have the current changing fast. Inductance is like inertia. So the formula for the amount of resistance, called reactance, is 2 pi. Well, they're just constants. The frequency and then the inductance. What's the inductance of the coil? Well, that has to do with how much wire there is, the size, the kind of materials. But F is the frequency. That's the important thing. Higher frequencies cannot get through coils, period. How about capacitors? They work the opposite way. There's a lot of nice stories about capacitors, but I don't have time to tell them. But capacitors block the low frequencies and let the high frequencies go right through. So the capacitive reactance, AC resistance, is inversely proportional to frequency. This is in the denominator. When the frequency is higher, the denominator is bigger, so the fraction smaller. Less resistance, less reactance at higher frequency. Oh, that's the opposite of the coil. So you can see here where I'm going. At some frequency, the resistance of the capacitor and the resistance of inductor have the same value. They have to. Something magic happens at that particular frequency. The two effects cancel each other, and the circuit behaves as if it has no reactance. Oh, see where I'm going with antennas. Antennas behave the same way. If they're too long or too short, they show up looking like capacitor and inductor. So if you get them just the right length, there's no reactance in your antenna, and resonance is easier to achieve that way. So, the ways you can hook these things up, series and parallel, all kinds of effects. I'm going to stop sharing.
Yeah, Barry, let's see if there's any Q&A here, and then we can probably do, just looking at the clock here, maybe about another 10 minutes on top. Okay, but let's see if there's any questions here, right? Over to you.
Okay, I'm not reading the chat, so was there anything that I should address?
No, and I'm not seeing anything here. Tom, are you looking at it as well?
Yeah, goes. I have a very pedestrian question. I don't use my NanoVNA every day. How often am I to charge the gadget to keep it in ship shape? That's this question.
That's a great question. I have no idea. I've had mine a year and a half, and I pull it out maybe once a month. I plug it in, and as soon as I plug it into the USB, it starts to recharge the battery. I think if I took it out for like field day and used it for 2 hours, when I got back, I would recharge it right away. But I have no idea. That's a good question. I have no idea.
Others? Yeah, Tom, I can't see it, so you got to help me out here.
I don't think there was anything more. Yeah.
You can open your mic if you have a question. So,
Tom?
Yes.
A comment about the power question. If the device, this is in general, it's not 100%, but if the device has an on-off switch, a hard on-off switch, Generally, lithium ion batteries will have half power after 1 year. If, on the other hand, the device has a soft switch, meaning a push button that you hold it for a while and it turns on, you hold it for a while and it turns off, something like that, that has a small drain on the battery, and that will last much less time in terms of recharge.
I would just pull the battery out. If you're not going to use it for a while, pull the battery out, and then you don't worry about that one. I don't know.
That's the way to do it, is just disconnect the battery and
Yeah.
you a year from
Or just
half
leave
power
it
out of
connected
battery.
to your computer on a USB port, so it's always charging.
Now, if you've got other types of batteries in your device, like NiCads or a couple others, they drain much, much faster, but lithium ion and lithium poly will hold up for about a year, half power.
All right, so let me jump to this. What I wanted to do was to investigate not antennas, because I can't mess with them. They're outside in my yard. And I'm not going to climb the tree. So I hooked up just a simple, resistor, capacitor, inductor. And I thought, well, how about if I just play with my Nano VNA with this circuit? Because I hooked these up the way this circuit is showing in series. So I have resistor, capacitor, and inductor. And I pulled these out of old tuners that I didn't need. I thought, well, let's see if I can tune it up for 80 meters, make a resonant circuit. Now, as a physics professor, I did a lot of this stuff, but with audio circuits, because it's a little less expensive and a little less dangerous. So, all right, so here's my capacitor. Okay, so I hooked the Nano VNA is off the screen here. What do I find? This, I didn't know. So here's the different graphs I can show in about 10 seconds on my Nano VNA using NanoVNA Saver software. I can do a Smith chart. I can look at what's called the reflection coefficient, or the log magnitude. The red is the through, the blue is the reflected. I can look at the phase going in and coming out, two separate graphs. And the phase is doing something really weird here. And I thought, oh, this is going to teach me about phase, because then I can play with the capacitor and the inductor. So the Smith chart, well, a year ago, I knew what a Smith chart was, but I'd never needed to use one. And I thought, oh, look at this, cool, but look, it's nowhere near the bullseye. Yeah, because I made one critical mistake. The Nano VNA in the input channel 1 has a built-in 50 ohm load. I didn't know that, and I added 50 ohms here. So I put a resistor where I didn't need one. Therefore, I didn't get even close to 1-to-1 SWR here. Okay, so I can plot SWR. I can plot something called return loss, which is an engineering term. If I get invited back, I'll show you how these are related. But the phase was the one that really got me interested. What do we mean phase here? Well, the Nano VNA is sending out a voltage, and it can measure stuff coming back. And if the voltage and the current are in phase, then at some particular frequency, I get resonance. And here's 5 degrees, -5 degrees right in here. The phase is 0, resonant frequency. Well, look, that's easy to spot, right? Around 3,600 kilohertz here. That's also where my SWR is lowest. That's where the return loss is greatest. So all these are related. And that's where the Smith chart is right here at this marker. So in just building this little simple, cheap thing and playing with it, I learned a lot about what the charts are telling me, and especially phase. Then I hook it up to my different antennas, and wow, this is an interesting one. Engineers could talk about this for an hour. The log magnitude of the S11 and the S21 curves. Oh man, this tells you so much. You're sending out energy and measuring how much comes back, but you're comparing it as a ratio, and then take the log of the ratio. So it's called the log of the magnitude of, and it's a ratio of input and output. So the blue is what's coming back, and I think the red, yeah, the red is the through signal. Oh, in a series circuit, what happens? At resonance, you get the maximum current. That means what? The minimum loss. Oh, now I get it. What if I want to look at resistance and reactance? Well, I can play with the circuit and then do these. Beautiful. So I don't want to explain all these. It'd take another hour, but I got to play with my little capacitor inductor, and here's the reflected phase. All right, so let me jump to one of these. So I had one of these and I thought, well, I kind of know how they work, but let's see. So you feed in NanoVNA energy here into the common, and you measure what comes out of each of these two ports. This port says 1.3 to 170 megahertz, 2 meters or below. This one says 350 to 500 megahertz, 440 meg, 70 centimeter. Does it work that way? So inside it has simple, not many parts, coils and capacitors, but it's, look, an OR circuit. It's a parallel. So here's the NanoVNA or your radio. Coils, 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 capacitors to ground. Oh, I get it. So what? The higher frequencies are going to ground. The lower frequencies get through. There's my 2 meter side. The reverse for the 440 band, 70 centimeter, only the higher frequencies get through. The lower frequencies get what? Shunted to ground. Let's see. Oh, here's what comes out of my 2 meter port. And this is with this little $50 NanoVNA. The gain that comes through, 0. Well, it's not an amplifier, but it's not attenuating either. So 0 attenuation up to about what? 200 megahertz. And then boom, falls off. So what's going to come out of this port is, here's 2 meters over here. Fine. Does the 440 energy come out? No, that's over here. That's annihilated by 30 dB. That's 1,000 times. How about the other port, the 70 centimeter port? What happens? 0 dB, no loss, no gain. So here's the 70 centimeter, 0 dB. So yeah, how about, is any 2 meter antenna come out of that port? That's over here. Oh no, look, it gets wiped out 60 dB. Oh, that's cool. So the device does what I expected it to, and it's like a $50 gadget, and look, it's the size of my fist. My favorite. I had this as a kid. There's a long story, but I don't have time to tell you. I was getting into my neighbor's television. I was 13 years old. Heathkit DX100, 100 watts. Man, I would wipe out, back then it was all analog, channel 3, 6, 10 in Philadelphia. So someone said, get one of these, Barry. So I got one of these, and you hook it up, coax in, coax out. It's called a Drake low-pass filter. I still have it. It's in my closet. I don't need it anymore. So I thought, all right, I'll attach the NanoVNA to this. What comes through this? Well, when I open it up, it's just simple coils and capacitors. Nothing special here except the name Drake. So, it's like $100 for the name Drake. Low frequencies below 40 megahertz get through fine. 80, 40, 20, 10 meters. But the TV channels above 50 megahertz to ground, to ground, to ground. So it filters out, it wipes out any harmonic energy from my Heathkit DX100. I had plenty of harmonics there. So here's the way I hooked it up. NanoVNA, input, the output back in. Look at this. Whoa. So 0 dB, again, no gain. It's not an amplifier. So no gain, no loss, up till about 30 megahertz. Perfect. Can use it all the ham bands. How about above 40 megahertz? Bloomp. Look at this. 80 dB attenuation. 80 dB. That's 100 million. Nothing's coming through on channel 3610. My TVI, television interference, eliminated. So whoever told me put on one of these filters, they were pretty smart.
Hey, Barry, we've got a question here from, in fact, I just lost it. Hold on. From Bill, WA2WL. Can you measure all 4 S parameters, is his question.
Oh. I'll have to try that. That's a very good question. I see no reason why not. See, S11 means going out 1 and coming back 1. S21 means going out 1, coming in 2. Oh, the answer is no, because it's only one port transmitting and the other port's totally receiving. Now, in that $100,000 NanoVNA, yeah. In fact, that really good one had 4 ports, and they're all in, out, in, out, in, out. So I think the answer to, I'll try it. I think the answer to that question is no. I can measure S11 and S21, and I think that's it.
Now, reading earlier up the string, Bill, N2BGR had a comment. Just the fact of be aware that some NanoVNAs are counterfeit. Make sure that it passes.
I don't know what
internal tests.
counterfeit means, because when you get them through different sources, they're all made somewhere in China. Mine, I didn't buy it, but the person who did bought it from Amazon. And I've heard others in the Philadelphia area say the ones they're getting from R&L Electronics are very good. So watch it if you just buy it. You know, for $50, there's a lot of factories knocking these out. Oh, someone said, does it come with a good instruction manual? I said, oh yeah, if you can read Mandarin, yeah. It had no instructions in English, nothing. Oh, and then someone else said, why don't you write the instruction manual? I said, no, thanks. Then anything that goes wrong, people are going to come back and my mailbox is going to fill up with complaints. No, thanks.
I bought a book for it. They offered a book on where I bought it, LG or whatever it is, electronic. They offered a book, a comprehensive book that's probably about 100 pages. I figure it would be a good idea to get the book with the device.
Or if you have a local club and a couple of you get on together and, you know, you share. That's the way I learned. You just share, play with the thing and share, you know. This Nano VNA presentation, when I gave it a year ago, had about 15 slides. Now I've got 150 slides. I've got too many.
Let's use a couple of minutes here for other questions that we have from the audience. Just, you know, unmute yourself.
I have a question.
If you have a question, go ahead.
Okay.
Identify yourself. Is that Steve?
Steve, WI2W.
Yes.
If you want to measure the other two S parameters, can't you just swap the ports?
No. S21 is what comes out port 0 and goes into 1. I think the answer, I said that too quickly. I think the answer is no. I'll try it, but I think the answer is no. Why would you want to do that is a better question. What experiment do you need to do or think about that you need to activate all 4 ins and outs? I can't think of how I would want to do that. All right, so I take silence as meaning, maybe that has no meaning to me.
Other questions? I see that Bill, again, N2BGR has a comment in the chat for everybody just regarding taking a look at some manufacturers. So just as an FYI. Okay. Other questions from the group?
KD2KLN already is voting for Barry to come back. So there you go.
That makes it easy.
So I thought I had about a little over 100 slides in part 1 and about 80 slides in part 2. That's obviously way, way, way too much. But I thought, well, this is interesting. This is interesting. So you end up with too much stuff. The thing that I learned about was if you have the time, well, look, I'm retired, so I have the time. Just get it out and play with it and try not to drop it. I mean, here's mine. So it's not the best of them that you can buy today, and it's not the best screen. But yeah, when I turn it on, if you have real sharp eyes, you might be able to read that. I didn't like playing with this device. So I securely left it on the table, attached a USB to my computer, and even my, you know, pretty crummy Windows 10 computer gave me all these beautiful charts. So here's what I wanted to talk about if I had 10 or 15 more minutes.
Get a 9 o'clock close right around in there. Over to you.
Oh, 9 o'clock, I'm just warming up. We call 9 o'clock here Quaker midnight, by the way.
Quaker midnight, that's right.
Yeah, okay. All right, so here's the beautiful part of this. And I've got a problem. I had an 80-meter antenna, and once in a while, not often, once in a while, I want to plug in a microphone and get on the MCOM phone nets at the top of the band. My antenna is tuned to 3600 kilohertz. Works really well there. When I go up to 3990, you know, like the Roosters net and stuff, and I get an SWR of, you know, 3, 4, 5 to 1. So can I QSY up to the top of the band? Here's the Smith chart of my 80-meter antenna. Here's the SWR. You can see it's above 3 to 1 on the phone part. What can I do? Oh, I know what I can do. I can cut off 10 feet. No, I'm not going to do that because then that won't work at the phone part. Oh, I could put up another antenna. Yeah, if I want to spend another $150. So there are a lot of ways you can broadband an 80-meter antenna, but it's not worth it. Here's the way you broadband an 80-meter antenna. You put a tuner in your shack. You don't need the tuner up at the antenna. Oh, some people do that, but then you need to waterproof it, get power to it. How does a tuner make my radio happy? Ah, that's part 2 of the talk. But essentially, in my shack, the coax has an impedance. Resistance, reactance, and impedance. it might not be an impedance close to 50 ohms, and my radio might balk and say, no good, no good. What if I put one of these, well, it doesn't have to be this gutsy, but this kind of a gadget. And then what do I do with these knobs? What's inside here? Just coils and capacitors. What if I tune this so the reflected wave that comes back from my antenna on my coax, the reflected wave, comes back into my shack. It hits this tuner. What does the tuner do? The tuner reflects the reflected wave. Now watch out. The tuner provides a reflection gain. No, wait. This isn't an amplifier, Professor. No, it is in a way. It takes the bad energy coming back and reflects it back to the antenna. Besides that, and now more power is aiming towards the antenna. Doesn't make the antenna any better radiating. The antenna still has the lousy SWR. But it takes the reflected wave and reflects it. And what does my transmitter see? 50 ohms. My radio is happy. It thinks it's operating into a 50 ohm dummy load, so full power. That's kind of magic. How does this work? That's part 2. The Smith chart is kind of the clue, the guide. Okay, so on the left is my original 80 meter antenna, and the center, 3.6 megahertz, is 50 ohms. After going through my tuner, here's my new Smith chart. Oh, it's awful here. Yeah, I know that. But it's really good at marker 3, 3.9 megahertz. So by fiddling with this, in my case, it's a manual tuner. By fiddling with the tuner, I've retuned the antenna system to be resonant at 3900, and my radio's happy, and I can get on and pick up the microphone and yak with my buddies. What happens when I now want to operate on the CW part of the band? Oh, and I forget sometimes. I got to retune my tuner to the CW part of the band. So that's a good place to stop. The antenna tuner does not make the antenna work any better, but it does make the radio deliver full power. Makes me happy.
Yeah, this is AC2ZU. I have an inverted V G5RV Junior.
Yeah.
The best I can get at SWR is 3-to-1, but I got an amplifier, an AO811H, and I'm told that the Pi network there will match it. You don't even need a tuner.
Now you got to be really careful how you said that. Yes, the amplifier, all tube amplifiers have a Pi network. They all do. Okay. What's the SWR on the part of your coax that's going up to the antenna? Is that SWR still 3-to-1 on your G5RV antenna?
Well, I use a NanoVNA. It's about 3-to-1 going from the coax up.
It does not. In other words, the amplifier Pi network will make the tube happy, yes.
Right.
But the SWR from the output of the amplifier jack up to your antenna, the G5RV, that's still the same lousy SWR. There's only, well, there are 2 things you could do to improve the SWR of the antenna.
Raise it up higher, right?
No, no, that's not what I was thinking. You said it's the G5RV Junior, right?
Right.
That's about 50 feet?
Right, 52 feet.
All right, what if you put up an antenna that was, let's say, 100 feet long? Make it twice as long. It also has that little section of coax and then ladder line.
Right, the ladder line, yeah.
Take the coax out. Just feed the whole damn thing with ladder line, which has very, very low attenuation. And then your tuner has to be able to tune to balance feed line. That will work a whole lot better, 80 through 10 meters.
I
The
understand.
G5RV, the Varney antenna, it's interesting. He designed that for 20 meters. It's 3 half wavelengths long, the full size,
Right.
102 feet. So it's 3 halves. It's low SWR and resonant on 20 meters, but only 20 meters. But it's fed with the combination of coax and
Ladder line.
ladder line. It's fed with a combination that the impedance isn't too awful anywhere. It's not very good anywhere except 20 meters. So take the coax out, just feed. In other words, make it you get as much wire in the air as you can and as high as you can, and just feed the whole damn thing with ladder line, but have a tuner that can match balance line, and everything will work better. The Pi network in your amplifier will make your tubes happy, yes. And the Ameritron amps, that little tuning capacitor,
Right.
it's the AL811.
Right.
Be very careful with that. The design is fine. The parts and the placement is little critical with that. Little. I know because I have one right over here. I have the H, the one with the 4 tubes.
Well, that's what I have. I have the H.
You know,
Good, good.
I've had mine for about 15 years. I use it mostly on 80 meters.
Mhm.
And I use it because I'm a net control on a net where I want, 400 watts instead of 40 watts.
I got a limitation in my backyard. I can only go like,
Yeah,
50
that's,
feet total. I'm limited as far as any antennas.
yeah. So in that sense, the G5 RV is sort of like, I don't want to be crude. My 67 Chevy half-ton pickup, 3-speed. It didn't do anything well, but it never broke down.
No, it gets out. It's getting out.
It climbed Pike
That's
Peak.
right.
I was in first gear, but it went up Pike's Peak.
It works.
Thank you.
Yes.
Thanks a lot.
Yeah,
Other
yeah.
questions as we sort of watch our clock here. So, questions or comments? I see this.
How many of you have one? That was my first question. How many of you actually have one? I can't see any. I'm seeing a lot of no's. Charlie, yeah. So those of you that have one, was it difficult to learn how to use? And did you hook it up right away to a computer interface like NanoVNA Saver, which is a Windows?
Yeah, the Saver is very good. I've used it. It's very convenient. You got 3 or 4 different charts. It's
Yeah, and it's easy. It's pretty intuitive, and you don't hurt anything. So part 2, if I'm invited back, part 2
There's
is
a number of people.
it's called reflection coefficient and return loss and SWR, and I have to show how those are related to each other.
Perfect. Yeah, if I can jump in too, I mean, there have been a number of comments about extending the presentation, which is, I think, are great, and having you back, which is great. We actually, I think, Barry, correct me if I'm wrong, I think we originally had this set up as a Saturday presentation. I think when we
Saturdays are really good for me. I'm a little
yeah,
more,
because this way it gives
at my
us a
age,
little bit more
after
time.
8 o'clock at night, my brain's gone fuzzy.
Well, yeah, you sort of think about that, but it gives us a little bit more flexibility in terms of what we might want to do with a
Now,
presentation.
the other thing I was going to do, but I couldn't because this is an older Windows 7 computer, I was going to hook up my Nano VNA and show you live what it can do with
Do a
different
demo, yeah.
antennas,
Perfect.
rather than, a passive slideshow. I can also send you the whole slideshow, and you can share it as a PDF.
Yeah,
any way you want.
and Tom has mentioned to a couple who have asked, is that, we're going to put it up certainly as part of our YouTube channel.
So I shared that with you, what, about a week ago or something?
Yep,
A couple days ago.
yep.
I don't know. And since then, I've re-scrambled all the slides. So
Don't
every
forget all-
time I look at it, I thought, oh, that slide out of place.
So,
But,
so our plan will be to get you back, okay?
Sure.
ASAP, and we'll look, and we can sort of play with the format as well too, which, obviously this is a presentation that really is, and can take as much time, as we have in terms of knowledge and also in terms of questions. So I guess
I'd have to add one more quick thing, and I don't
Sure.
mean this to be demeaning to anybody. When I was a teenager, I got my extra ticket by memorizing answers to questions. I understood nothing. I mean, nothing. And back then I had to draw circuits of a Colpitts oscillator with a blah, blah, blah. And I knew you draw a circle, you put dots and a little squiggle, it's like Shakespeare. I memorized how to pass the test. I didn't know a thing. If someone said, how does a transistor work? I wouldn't have the faintest idea. I couldn't tell you. So over the years, and especially, becoming interested in physics, I wanted to learn really the guts level. So when you look at like a Nano VNA, I'm trying to see, how do you explain how it works at a gutsy level rather than up here? Let's start down here. Resonance, 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 phase, 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 Grampy and grandchild. That's what helped me getting the analogies rather than talking about impedance of an antenna. It's like, it's a bunch of words. What does that mean?
That's what learning's all about, right?
Why do antennas have any impedance at all? I had an interesting discussion, argument with an engineer about what is resistance. This is at one of these talks, and I forget that the topic got a little off, and he said, so blah, blah, blah. And I said, what do you mean by resistance when you use resistance? And so we got off topic a little bit. Are there any RF engineers in this group?
Anyway, well, thank you, Barry. I think this has been really great, as always.
It was
and
fun.
obviously, we had 50 people, okay, at our peak, and which is really terrific. And we've had visitors from India with Sudipta. We also had a visitor today from the UK, Elliot M0JBY,
Oh
part of the
man,
Chelmsford Amateur Radio
it's
Club.
like
where-
it's
where
like 3
G5
a.m. there.
Yeah, where G5RV was actually a member of the Chelmsford Club, if my memory.
Oh well, yeah, party, yeah.
So yeah, so we're really, really glad to have all of our visitors tonight. We'll get back to you all as part of our speaker program, Coffee Talk program, in terms of bringing Barry back, okay, for part 2. And also, if you have any questions or comments, you could forward them over to me, and I'll send them over to Barry as well. And that's wx2r@arrl.net. So anyway, I guess if there's no final comments, Barry, thanks very, very much for a great night. Okay, and we'll see you back again soon as a friend of our club. So great presentation.
Thank you for the invitation. Good evening from Philadelphia.